In this video, we are going to review a little bit of implicit differentiation. We are going to start chapter 3. So in this example, it says if we have this equation, and you'll notice that the x's and y's have all been mixed up, to find y prime at the point 1, 1, here is my suggestion. So what you want to do is we want to use implicit differentiation because the x's and y's are all mixed up. It's not explicitly solved to say y equals in terms of x. So we're going to get 3y squared y prime plus, now use the product rule, so put a little dot maybe between those, first times the derivative of the second plus second times the derivative of the first. The derivative of 6x is just 6. The derivative of a constant is 0. Now, if they were actually letting me solve for y prime, if they wanted y prime in terms of x and y, I would have to do more algebra at this point. But since they are telling us that this is happening at the point 1, 1, every place that we see an x or a y, replace it with 1. So we get 3y prime plus 3y prime plus 9 plus 6 equals 0, which is 6y prime equals negative 15. So y prime is negative 15 over 6. They're both divisible by 3, so that's negative 5 over 2, which is C. Just what you see right there, okay? Okay, in this lesson, we are going to talk about using derivatives to find minimums, maximums, and critical points. You might recall we have seen this where this moves along, and if it hits a spot where it's decreasing, it turned red. When it hit a spot that was increasing, it turned green, those slopes of those tangent lines. And then we also found that at these maxes and mins, that the slope of the tangents were always 0. It turned black in the original video. So that's going to be helpful as we go through this process to remember those things. So here it says if a function f has an absolute maximum or a global maximum, then f of c is greater than f of x for all x in the domain. At that value c, see how f of c is larger than all the other f of x's. If it's an absolute minimum at c, then f of c is less than all the other f of x's on the domain. That's if you use the word absolute, okay? We're going to call those values extreme values. So although our quadratic has an absolute minimum at its vertex 0, 0, the x cubed does not have any. It has this kind of strange switchover we see at 0, 0, but it is not an absolute max or min. So if we look at this graph, let's categorize the local mins and maxes. Are they absolute? Are they local? Well, what are they? Okay. So let's put a little dot at all of the places we have indicated here, okay? So our endpoints of a continuous function could possibly be an absolute max or min. It just depends upon the function. They will not be relative because we don't know kind of what's going on either side of them. But this particular spot at the point a, f of a, we have a local, or I'm sorry, an absolute minimum. It is the lowest of the entire function. Here, this point here is a top of a hilltop, but that would be a relative maximum. This would be a relative minimum. Relative to the points around it, it is the lowest. Relative to the points around it, it is the highest. This one here, yes, we can always say it's a relative maximum. Relative to the points around it, it is the highest. But actually, this is the absolute maximum because for all x's along the domain, it is the highest. And then this is a local minimum. It's not the lowest, but it is a valley in the graph, a low point of the graph relative to the points around it. And then this is not anything particular. Okay. So a local min or a local max were relative in a very small interval around this C value. We are at a high point or low point. So this is a local maximum. This is a local minimum. This is a local minimum. Now, even though this is the absolute max, it can be considered a local max. This is only they are or they are not absolute maxes or mins. So there's that. So let's take a look at our graphs of these and let's see what we can see. Okay, so our cosine graph looks something like this. I'm going to call this 1 and a negative 1 and 1. So our cosine graph looks something like that. The local maximums are also the absolute maxes of these points. And you'll notice they happen on the even pies. So we can say that the absolute maximums occur at 0, 2 pi, 4 pi, negative 2 pi, etc. Now mathematically we should write that as an even, so we say 2n pi when n is an integer. Okay. What are our absolute minimums? Our absolute minimums occur at the odd pies. So how would we write that? So, you know, like 1 pi, 3 pi, negative 1 pi, negative 3 pi. And we would write that, to write an odd number formally, you would just write that as 2n plus 1 pi when n is an integer. Okay. And then we already saw the graphs from before. Our x squared graph has a local minimum, which is also absolute. Our cubic function has no maxes or minimums. We're just looking at some graphs we already know. But let's look at a polynomial. So we have a polynomial to the right. We've looked at that polynomial. We have pinpointed, you'll see how they're only looking at the graph from an x value of negative 1 to an x value of 4. They are including the endpoints. So you will notice that we have a few things that have happened. This endpoint is our absolute maximum for the graph. This endpoint is nothing special. This is a bump where we have a maximum, but it's not the highest point of the entire graph, so that is a relative or local maximum. This is a minimum of the graph, but it's not anything super special. So that is a relative minimum. This one, yes, you could categorize it as a relative minimum, but it is the lowest for the entire graph. So we're going to call this one an absolute minimum. Now, back in a pre-calculus class, we had to really fight to find those values. In a calculus class, we want to be able to find them a little more algebraically. We want to be able to graph things, find these very special points about our graph very easily. So the extreme value theorem can help us. And it says if f is a closed interval from a to b, and f attains an absolute maximum or an absolute minimum of some numbers, then those numbers are going to be called or categorized as extreme values, we can call them. And it basically says there will be, it attains an absolute maximum or an absolute minimum on that interval. So again, let me say, if we have a function that is continuous on a closed interval from a to b, there has to be an absolute max and an absolute min somewhere within that interval. Now, it can be on the ends or something in between. It could have multiple places, okay? So let's look at these three. Now, these are continuous. We do not have to lift our pencil. They include the ends. So that's what they're talking about in the extreme value theorem. So this one has a max at some c, somewhere in the middle. It has a minimum, absolute minimum, somewhere in the middle. In the second graph here, the absolute max is in the middle, but the absolute min is on one of the endpoints. For our third graph, we have absolute maxes in the middle. We actually have two of them, but we have an absolute min also in the middle. So an absolute max and absolute minimum of a function that is continuous on a closed interval must occur. We have to have some maximum somewhere along that interval and some minimum somewhere along that interval. So if you look at this function, the reason we cannot say that it has a max or a min is because it does not fit the extreme value theorem. It is not continuous. Same thing here. It is not continuous. We haven't included one. We haven't included this because of the asymptote. Here we haven't included that. So we have that disconnect here. We have that asymptote here. So that's why these ones don't fit into this category. So the extreme value theorem only works if we have a continuous function on a closed interval. There will be a maximum value somewhere and a minimum value somewhere. So that's what we're trying to find here. And Fermat's theorem is an extension of the extreme value theorem. And it says that if it's a local min or max, it has to have had a first derivative that existed and was equal to 0. So that's the kicker. Now let's take a look at here. Our first derivative equals 3x squared. We know that if we look at that function, yes, the first derivative equals 0 at 0. And if we looked at the graph of that function, it did not have a local min or max there. Fermat's theorem does not say every time you have a derivative that equals 0 that you're going to find a local min or max. It says if your function has a local min or max at that value, then the first derivative exists, and then the first derivative equals 0. So that's what you have to be careful of. Let's look at 6. If we look at the first derivative, if we rewrite that, remember, as a piecewise function, the first derivative of that is -1 when we're less than 0 and +1 when they're greater than 0. So if you look at our derivative, because of this strange thing that happens, got my equal to there, uh, that again isn't a good way for Fermat's theorem to help us. Okay. So that leads us to critical numbers. What are critical numbers? Well, a critical number is where the first derivative equals 0 or the first derivative does not exist. So highlight that. A critical number is where the first derivative equals 0 or the first derivative does not exist. Okay. A local min or max has to occur at a critical number. That's why this sentence here is so important. If a function has a local min or max at C, then C had to be a critical number. So if we can find the critical numbers, then we can find the possibilities of where our local mins or max could occur. Okay, so let's look at this next function. So this function requires that if we do the derivative, we have to distribute to make it prettier. So before we get started, let's go ahead and let's do a little rewrite. So that would be 4x to the 3 halves minus, now that would be 5 halves plus 3 halves. So that would be x to the 8 halves. Not 8 halves, I'm sorry, 8 fifths. Our derivative, let's drop the 3 fifths down in front. That's 12 fifths. Power goes down by 1. Drop the power down in front. Power goes down by 1. Okay. And so let's think about what the critical numbers are. So you have to ask yourself, where does that function not exist? Well, this second piece right here, that is really x to the 2 fifths in our denominator. So x to the 2 fifths equals 0 when x is 0. So that's out. We can't have a 0 denominator. So we definitely have a critical number when x is equal to 0 because the first derivative doesn't exist there. So that's our first critical number. Our next critical number is where this quantity is equal to 0. So let's focus on that for just a second. Let's multiply everything through by an x to the 2 fifths so that we can bring that x to the 2 fifths out. And let's actually multiply by 5 too to get rid of our fractions. So when we do that, we get 12 minus 8x to the 5 fifths, or x, equals 0. So negative 8x equals negative 12. So x equals negative 12 over 8, or negative 3 halves, or negative 1.5 is another critical number. Okay, so let's go into Desmos. At least I'm going to do my best here. Let's put that function into Desmos as it was originally written. So that was x to the power of 3 fifths times the quantity of 4 minus x. And then let's put in x equals 0. That was a critical number. And then let's put in x equals negative 3 halves. Why don't we keep, oh, that was right. I'm sorry. And then let's look at our function for a minute. Oh, so a negative divided by a negative, Mrs. Hott, is a positive 3 halves. And I found that because at my graph, I have that little peak there, and it sure isn't at negative 3 halves, but it is at positive 3 halves. So let's kind of zoom into our graph where we hit. We have critical number at 0 and a critical number at 1.5. If our function has a local min or max, It has to occur at one of those. There is a local max at 1.5. Now, 0 does not have a local max. There's some other interesting things that we'll eventually talk about that's happening to this function at 0, but it's not a local minimax. Okay, so that is that. Now let's talk about the finding the absolute maximum of a continuous function on a closed interval. It's called the closed interval method. The first step, now I'm going to summarize underneath this. So this is finding absolute max and min of a continuous function on a closed interval. Okay. First thing you do are you find the critical numbers. I'm going to call those CNs from A to B. Okay. Second thing we do is we're going to plug in the endpoints of the interval. So we're going to find f of A and f of B. Now we're plugging them into the original function. And then you're going to plug in the critical numbers we found into our function. And then you're going to compare. What are the largest? What are the smallest? And then go from there. So we're going to find the critical numbers, and we're going to plug those in. We're going to find the endpoints, and we're going to plug those in, and then we're going to compare them. Whatever we get, those are going to be the absolute maxes and mins of our function. So if they ask us to find the absolute max and min of a function, and they have specified a certain interval, did they include the endpoints? Yes, check. Is that a continuous function? Does it have any breaks or problems within that interval? No, it's a cubic. Cubics are great. It's a polynomial. There's no breaks, jumps, so we can use the method we saw on the last page. So we need to find the first derivative, which is 3x squared minus 6x. So we need to find where the critical numbers are. Remember, that's where our first derivative doesn't exist or equals 0. So we're going to do the equals 0 for this one because it's a polynomial and our derivative is a polynomial. So we got to just set it equal to 0. I'm going to factor out of 3x. I'm going to get that we have critical numbers at 0 and at 2. So let's plug in 0 and 2 into our original function. If you plug in 0, you get 1. If you plug in 2, you get 8 minus 12 plus 1, which is negative 3.
Is this deep enough for the...
Yeah.
This is like 14.
Yeah, that would look good. Yeah, that,
I
like
no,
that.
I can go do 18
No.
off the other,
No,
off the other one.
I like that. So next, let's plug in our endpoints. And again, I apologize if I am not doing these exactly in the steps they said on the other side. But if we plug in our ends, we get, let's see here, we get negative 1/8 minus 3/4 plus 1. Let's get a common denominator. That's negative 1/8 minus 6/8 plus 8/8, which is 1/8. And then let's plug in 4. We get 64 minus 48 plus 1, which is 17. So our third step is what's our max? What's our minimum? So So let's go back up and look for the largest value. Our largest value, that is our absolute maximum on that interval. That is our largest value. This is our smallest value, so that is our absolute minimum. So we should be able now to graph it. So if you graphed it, went into Desmos or something like that, and graphed it, look at our lowest point. Our absolute min was at the point 2, -3. Our absolute max was on one of the endpoints at 417. So that's the method you want to take if they ask you to find the absolute max or min of a function on a particular interval. So now let's do a word problem. It says the Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at time 0 to jettison at 126 seconds is given by this function. You'll see it's our velocity function. Use this model to estimate the absolute max and min values of the acceleration of the function between liftoff and jettison. Okay. Now it says we want to find the absolute max and min of the values of the acceleration. Okay. So we need our acceleration function. Now we have to find the max and mins. Our interval is from 0 to 126. Okay. So it becomes a problem like the last example. Okay. So the first thing we have to do is find our derivative. So 0.003906 times 2 is 0.007812 t minus 0.18058. Okay. Now we need the critical numbers that occur there. That is a linear function. It will only have a critical number where it's equal to 0. So let's set that equal to 0. And so if we divide that 0.18058 by 0.007812, let me tell you what we get. We get approximately 23.1 seconds. We have a critical number, okay? Now, we had two other numbers we have to check, the endpoints, 0 and 126. So we're going to go back to our acceleration function. We're going to plug in 0, we're going to plug in 126, and we're going to plug in the 23.1. Okay. Do I have to do the calculus in this house? Probably not, probably not. Probably. Fuck off, dog. When we plug in 0, we get 23.61. And that would be meters per or feet per second squared. Okay. If we plug in 126, we get 62.87 feet per second squared. And if we plug in 23.1, we get 21.52 feet per second squared. Okay. So at 0, it's kind of right in the middle. At 126, it reaches its maximum acceleration. And at 23.1, it is at its minimum acceleration. Okay, so that is an example of an application of this. So there is your assignment. Good luck. Thanks.